how do you build a perfect bee? One that is productive, durable, can resist viruses and diseases, and can adapt to a changing climate. Well, I'd say Mother Nature's done a pretty good job creating bees with many of these traits. But evolution can take time, and today's bees are facing so many challenges. Both old ones like diseases and predators, and new ones like pesticides and different foraging patterns. Humans have been breeding honeybees for centuries to help them adapt to new environments. And with technology improving at a rapid pace, breeders may now have the tools to build a perfect bee.
In a sense, breeding has happened on varying scales for hundreds of years, for sure since the 1800s, especially in parts of Europe. And one of the challenges that they faced was that they didn't have the capabilities or capacity to do artificial inseminations like we do.
That's Dr. Liz Walsh, a research scientist at ARS's Honeybee Breeding, Genetics, and Physiology Research Lab in Baton Rouge, Louisiana. Walsh works closely at the lab with ARS research leader Lainey Bilodeau, using artificial insemination to breed honeybees that can adapt to the environmental challenges of today.
You think of artificial insemination as cows or horses or things like that, but we actually can do this on honeybees as well. And it takes very tiny instruments, but we breed bees that have traits that we want to propagate, that we want to carry on to the next generation to try to improve these traits.
One of the biggest accomplishments of the breeding lab here has been breeding bees for resistance to the highly destructive varroa mite. As mentioned earlier in the podcast, the varroa mite can spread deadly viruses between honeybees, causing entire colonies to die.
We have a long-standing breeding program for varroa-sensitive hygiene, and it does give the bees really good varroa resistance. So we will pick those queens that have colonies with the very strong expression of that trait, and drones as well from different colonies, and then we will breed them with artificial insemination.
Bilodeau and her colleagues not only breed for specific traits, such as varroa-sensitive hygiene, or VSH, but also for general characteristics that make them healthy, robust, and productive. For example, they successfully bred Russian honeybees brought over from the Primorsky region near Siberia. These honeybees score well for not only varroa resistance, but production as well.
One advantage that they have against the varroa mite is that they were right next to the original species that varroa parasitized. And so evolutionarily, they were right there, right next to it. So they came with these mechanisms to deal with the varroa mites.
Breeding may be quicker than evolution, but that doesn't mean it's easy. Researchers face many challenges when trying to breed for either specific or general traits.
Some of the challenges are that you can breed for a trait and you can get too much of a good thing. In the course of the VSH breeding program, when you bred solely for VSH and you didn't outcross any of the bees, the genetics got a little squirrely and the bees just cleared everything out of the colony. That can be a problem. You can breed too far. We have to make sure that we have the genetics diverse enough that we don't have those problems. Another thing is that we want to avoid inbreeding. That's a very big issue because in honeybees, particularly if we have inbreeding, then the brood dies because we get diploid drones and they are not sustainable for the colony. So they end up dying.
Despite these challenges, researchers here have a record of success breeding honeybees with traits that enable them to adapt to a diverse ecosystem.
We're working on nutrient assimilation so that the bees can more effectively use the nutrients in the food that they're eating. We're looking at general resilience, and we're looking at other resistance traits, disease resistance traits, and traits related to queen health.
They're also continuing to work to combat the varroa mite, which remains one of the biggest threats to honeybee survival.
We're trying to get at what's driving it so we can look at the genetics of that and then use genetic markers to help us speed up those breeding efforts. We're really getting into the nitty-gritty of it now because we have some very highly skilled scientists and the technology has gotten to a point where we can take advantage of that for breeding that next better bee.
Climate change is on the minds of all ARS researchers, and bee breeders here are no different. In the case of honeybees, Climate change is altering blooming seasons. For example, a warm winter may cause flowers to bloom while the honeybees are winterizing. This causes the bees to come out during their resting phase to look for food, but there's no food available.
That's a big problem that's affecting the entire beekeeping industry and even native bee populations, all the bees. Flowers are blooming earlier, or in some cases they're blooming later, but it's not timed right because the bees need to build up energy to go into winter. And they need certain things from those plants to go into winter. They need things that they can build up good energy storage. And then in the spring, they need certain flowers blooming when they come out, when things thaw. We want to work on these bees and help them have better ability to overwinter so that they can have these energy stores.
ARS researchers are working on alternative nutrition sources that beekeepers can feed their colonies during the winter. One food source is microalgae, which could provide nutrients to help bees boost their immune system to fight off viruses.
One of the real benefits of using microalgae is that it's sustainable and it is scalable. It can potentially be grown in huge vats and it would be fairly easy to produce.
This is Liz. I think beekeepers need to know what's going on in their colonies and be aware and familiar with the environment. Bees need a certain specific number of amino acids and proteins that are found in pollen, and they also need a robust amount of carbohydrates, which are found in nectar, to continue to be healthy and to survive. Hopefully, those needs are met in the environment, but if they're not, the beekeeper has to both be aware that the bee's nutritional needs are not being met and be ready to intervene with additional food.
I can't really blame bees for going out looking for food when they're hungry. I mean, we all get a little hangry at times, and bees are no different. Or are they? Actually, Walsh is looking into that.
I have the pleasure of being in the second year of a really exciting study that I call the Hangry Bee experiment. What we're doing is we're simulating pollen dearths at a single apiary location, and we're seeing how it affects the bees on both a behavioral and a molecular level.
Basically, what they're doing is allowing bees to venture into an apiary where food is available. And for half the bees, they can bring the food back to their colony. But for the other half, Walsh installed traps that rob the bees of their pollen as they exit the apiary.
And we found that pollen dearths do affect honeybee temperament. So in particular, aggressive responses are higher in bees that are hangry, if you will, that have been pollen deprived. And the molecular mechanisms behind that we're still exploring.
The bees that were hangry showed aggressive behaviors, including stinging, pursuing a potential predator, in this case Walsh, and clinging tightly to one another, another form of agitation.
We also see colony-level effects that include decreased brood production and lower population levels.
These observations can be shared with beekeepers to recognize signs that their bees may not be getting enough food or nutrition. The study may also help researchers breed bees that can more efficiently collect and store food, another step towards building the perfect bee. Speaking of which, I asked Bilodeau how she envisions building the perfect bee.
I envision that we can layer traits on top of each other. So not just have a bee that is just furrow resistant or just virus resistant or just really uses its nutrients, but that we can layer these things on top of each other. And that's tricky. But right now, we're just developing those lines, and then we're going to see how they play together. I think that best bee of the future is going to be able to resist viruses and resist pesticides, because that's definitely an issue. We need these bees to be able to be tough, and they need to be able to survive all of the onslaught that they have and to be able to be flexible with the effects of climate change. So that resiliency, I think, is kind of the key, right? So it's got to come back to just building a stronger bee.
I hope you enjoy this podcast on honeybees and other pollinators. They're so important to our ecosystem and our livelihood. To find out how you could help honeybees, visit your local extension service or go to our Science in Your Shopping Cart website to find your local extension. For Science in Your Shopping Cart, I'm Todd Silver. Thanks for listening.
Science in Your Shopping Cart is produced by the Office of Communications, Agricultural Research Service, an agency of the U.S. Department of Agriculture. For more information, visit www.ars.usda.gov. Follow us on Twitter, LinkedIn, and Instagram, like us on Facebook, and watch us on YouTube.